let's now take a look at some specific IV equations for our MOSFET. So the derivation of these equations is beyond the scope of this class, but we're going to go ahead and just write them out, and we're going to make sure we're comfortable with using them. So let's be clear that right now we're looking at equations for our NMOS devices or our N-channel devices. We're going to come back and we're going to talk about PMOS in a little bit, and as you might expect, it's basically the same with some minor changes to polarities and current directions. So our NMOS has, of course, our two operating regions when we're not in the cutoff. So the first one is our non-saturation region, or as we said in the previous video, sometimes it's also called our triode region or our ohmic region. So this non-saturation region is defined by VDS being below our VDS sat. And so of course, remember our VDS sat is just equal to VGS minus VTN. So in this non-saturation region, it turns out that our drain current, ID, is equal to Kn times 2 times the quantity of VGS minus VTN times the drain to source voltage, VDS, minus VDS squared. So let's close our brackets. All that's multiplied by K sub n. And we're going to come back and define that K sub n here in a minute. So that's for our non-saturation region. The other region, of course, is our saturation region. And so that was if we're above VDS sat. So now we have VDS is greater than VDS sat. And so in this region, it turns out that our drain current, as we said before, is ideally independent of VDS. So we have Kn times the quantity of VGS minus VTN squared. And so again, this is the ideal case. We're going to come back and we're going to modify this a little bit later, because what we're going to see is there is some dependence on that VDS value, even in the saturation region. And so it's a similar sort of idea as we looked at our early effect with our BJT transistors. So let's come back now and let's define this K sub n. So we see both of these equations have this K sub n parameter. So what is this? So it's something called our conduction parameter. So K sub n is our conduction parameter. And as we define this, we're going to see we're sort of opening up a whole can of worms, and we're going to have to define a lot of other things as well. So our K sub n, capital K sub n, is equal to W, which is the width of our channel, times mu sub n times Cox prime, divided by 2 times L. And so oftentimes you'll see this rewritten as a lowercase k sub n prime divided by 2 times W over L. So let's define some things in this equation clearly, just to make sure everybody's on the same page here. So the W, so let's start there. So our W, as I said, is just our channel width. And so you can refer back to our figure where we were looking at our MOSFET, but essentially this is the width from the front to the back of the gate. Since we're talking about width, let's go ahead and talk about that L in the denominator, which is our channel length. And so our channel length is just the distance between the source and the drain. And so remember, oftentimes this is referred to as the critical dimension, or CD, and it's usually used as a metric for the generation of the device to say, you know, oh, this is a 14 nanometer device. So that 14 nanometer is this gate length, or the channel length, we would say. So we also have this mu sub n, which we should recognize from our semiconductor physics. So that's going to be our electron mobility in the inversion layer. So this is electron mobility in our inversion layer. And then we also have this Cox prime. So our Cox prime is going to be equal to the permittivity of our oxide, which is the relative permittivity times our permittivity of free space, divided by our Tox. And so it's actually not the capacitance of the oxide, but the capacitance of the oxide per unit area. And so that's what the prime indicates, that it's per unit area. So oxide capacitance per unit area. So then finally, what is that lowercase k sub m prime? So lowercase k sub m prime is equal to mu sub n times our Cox prime. So we've just sort of simplified that a little bit. And this is something that we'll refer to as our process conduction parameter. And so the reason that I wrote this equation up here in sort of a slightly different way, is that we can see our process conduction parameter, our lowercase k sub n prime, which we've defined down here, is dependent on the electrical characteristics of the device. So our dielectric permittivity, for instance, the dielectric thickness, our electron mobility in the inversion layer. So we have some dependence on our electrical characteristics of the material. So electrical characteristics. And then we also have this W over L. So we see we also have some dependence on the actual geometry of the device. And so that's why oftentimes you'll see that equation sort of broken out in that way. And so note again that that conduction parameter, capital K sub n, is appearing in both of these ID equations for our non-saturation and our saturation region. And so it turns out that that lowercase k sub n, so if we're looking at this equation here, that lowercase k sub n is usually fairly constant for a given fabrication technology. So fairly constant for a given fabrication technology or fabrication process. And so what that leaves then is that width to length ratio as being a main design variable. So this means that that W over L is our main transistor design parameter when we're dealing with MOSFETs. And so we'll see that a little bit later on in this class, as well as in some other classes when we look at some more complicated circuits.